Thanks very much indeed, Sean. It's always great to be back in Dublin, and I'm amazed that so many people are here when you could be outside with a cold beer. But I'll hopefully it will make it worthwhile. What I'd like to talk about this evening is sleep and light and these body clocks, these rhythms, these 24-hour rhythms that we have that regulate so much of our physiology and behavior. We've got until about 7:30, and I'd like to make this as informal as possible. So if I say something that's incoherent or stupid, then stop me, wave your arms, stop me, we can clarify and then go forward. Or if there's a burning question that you have as we're going along, let's make this much more like a sort of tutorial rather than a formal lecture. What I thought I'd cover tonight is, first of all, sort of an introduction to the world of 24-hour rhythms. The fact that our biology is not constant, but is constantly being adjusted over the 24-hour day and changing. Then move on to how these 24-hour rhythms are generated and how sleep, which is a very important form of these daily rhythms, is generated. Then consider how light and the detection of light for the regulation of the internal day, internal time, is so important, and the discovery actually of a completely new light sensing system within the eye. Then talk about some practical applications of this knowledge in shift work, but we'll talk a little bit about teenagers, and I notice there are a few teenagers in the audience, so you might be able to sort of share your experiences of being a teenager. And then finish with some discussion on a very new area, which is the relationship between mental illness and sleep and circadian rhythm disruption, and some really exciting new areas of research that have emerged there. So let's kick off with this world of 24-hour rhythms. And of course, not to insult your intelligence, but we live on a planet that revolves once every 24 hours. And that 24-hour revolution causes huge complexity to our world. Massive changes in light and temperature, availability of food, the whole lot. And what's happened is that essentially all biology on the planet, almost every organism, has a way of anticipating this 24-hour revolution and fine-tuning physiology to the varying demands of the light-dark cycle of activity and rest. So if we look at our own species, and we can take any parameter you want, whether it's mood, core body temperature, blood pressure, whatever, we see really marked changes from the middle of the day and the middle of the night. And the point I want to stress is that these rhythms arise from within. So if you and I were taken to a dim, dark cave, constant light, constant temperature, we'd still see these 24-hour changes driven from an internal clock. What's so important, though, is that these internal rhythms have to be locked onto the external world, and we use the light-dark cycle to fine-tune this varying dynamic physiology to the demands of activity and rest. So let's burrow in and look at some of these rhythms in a bit more detail. And well, the first observation, I guess, is let's look at core body temperature. What you see is that it's not a square wave. What we see in core body temperature, that in anticipation of going to sleep, core body temperature is dropping, and then in anticipation of waking up, core body temperature rises. Now, clearly, if one exercises, then you can raise core body temperature, but it's on this moving, internally generated baseline. And this change of about a degree has real impact on, for example, athletic performance. Are there any athletes here? Any athletes? Hands up. There's somebody smiling. Sir, you're smiling as though, yes, I am an athlete. Nodding, yeah. But all right. Okay, if you don't want to admit it. So if there were an athlete, and particularly swimmers in the audience, then this change has a real impact on their ability to perform over the 24-hour day. And these are some real data. So we see time of day here, and then one's swimming performance. And in the early hours of the morning, you're slower, and in the evening, you're faster. And it's a big difference between this time here and this time here. A swimmer can swim 100 meters 2.7 seconds faster in the early evening compared to the training sessions in the pool in the morning. Now, 2.7 seconds doesn't sound like a lot, but of course from the Olympics you'll have seen that 2.7 seconds is the difference between coming first and a really embarrassing, appalling last. And this sort of illustrates the point that when you push our biology to the extremes, these changing rhythms can have a big effect upon performance, athletic performance in this case. Let's look at another rhythm, our blood pressure. Systolic blood pressure really shows big differences. You know, we're told that perfect blood pressure is what, 120 over 70, 120 over 80. But in the early hours of the morning, blood pressure can drop, systolic pressure can drop to almost half. It can drop to, let's see, about 70. And then in anticipation of activity, blood pressure is cranked up, and we've got increased blood pressure ready for the activities of the day. This has a real impact on the incidence of stroke. So a stroke is the build-up of a clot in a major blood vessel going to the brain. The clot becomes dislodged and gets caught in one of the branches of the blood vessels going to the brain. The brain is starved of oxygen, and then you have brain damage. Now, if you look at the frequency of stroke, it's very marked. So here we have time of day, and we have the frequency of having a stroke on this axis. This is from my colleague, Peter Rothwell. And you see that between 6 a.m. and 12 noon, there's a 49% greater chance of having a stroke than any other time of the body, time of the day. And of course, what's happening is you've got this internally driven rise in blood pressure coupled with activity, dislodging all of those clots. They fly into the circulation, get lodged in the brain, and this is when you have your stroke. So tomorrow, when it's 12 o'clock and you look at your wristwatch, you can say, phew, I've survived the most dangerous part of the day. And it's true. I mean, you know, it's really quite marked. But this has real implications, of course, if we're thinking about the timed application of medications that would dissolve those clots, then clearly you'd be taking them here in anticipation. You dissolve them before you actually sort of wake up. And so this sort of knowledge is now beginning to inform the timing of different drugs. Let's look at another one, alertness. Now, we see big changes in alertness over the day. And this is not just fatigue. This is what you'd see if you were lying constantly, dim, constant conditions, constant temperature. There's a big change. Now, I think intuitively, we'd all know that we're not at our best at around about 4 o'clock in the morning. But there's some lovely data illustrating how impaired we are. So on this axis here, we have a drop in our ability to perform various tasks. I think in this case, it was some sort of mathematical task. And in this first experiment, they compared the drop in brain performance with increasing levels of blood alcohol. So people were given free alcohol, and then their ability to perform these tasks was monitored. And you see, and I know this will be a big surprise to many of you, that as you consume alcohol, your ability to function drops off. Now, in the UK and Ireland, a blood alcohol level of 0.085 is when you're legally drunk, and you show a drop of around about -15. Now, let's look at the same cognitive tasks, the same brain tasks, but just with time of day. So during the day, there's a slight dip in the middle of the afternoon, but at around about 10 o'clock at night, our ability to function drops very markedly. But look at this. 4 to 6 o'clock in the morning, our ability to function is worse than if we consume sufficient alcohol to make us legally drunk. Now, as I say, this isn't fatigue. These people were kept awake throughout this whole period, but we know that this isn't as a result of getting tireder and tireder, but is an endogenous driven rhythm, because, of course, these people here have been awake far longer than these people here, and yet their ability to function is increasing. So if you take absolutely nothing from this lecture, then the fact that if you're driving a car at this time of the day, your ability to drive that car is worse than if you got in the car with a few whiskies or a few beers inside you. And the data that support, this is the trend of accidents over the 24-hour day and accounting for traffic volume. And you see that these early hours of the morning, there's a much greater, it's about a 5-fold difference in one's ability, in one's chances to have a motor vehicle crash in these early hours of the day. And as I say, it's part of that internally driven change in our ability to function. Let's look at one final rhythm, which is sleep. Sleep is perhaps the most obvious and the most profound and robust rhythm that we experience, 24-hour rhythm we experience. but we ignore it. It is really remarkable. Let's just look at some of the statistics, the importance of sleep. 36% of our lives are spent asleep. So if you live to be 90, then I think, well, if I do a quick calculation, 32 years of your life will have been asleep. Now that huge amount of time is telling us that sleep is doing something important. And if you compare the percentage of time sleeping compared to other things, work-related, watching TV, eating and drinking, household work. I have to say I'm not sure that I'm convinced that 8% of my life is dedicated to household, particularly when the kids come home. I just abandon it. I mean, the house just gets trashed. The point I'm trying to make, though, is that this is a huge amount of our time, and we simply ignore this important biological rhythm. And our attitudes towards sleep are so profoundly different now compared to our attitudes in a pre-industrial age. Just worth reflecting upon what people thought about sleep in Shakespeare's time. Shakespeare, loads of references to sleep in those amazing plays. Enjoy the honey-heavy dew of slumber. I mean, it's just so wonderful, those words. They really enjoyed sleep. Another one from Macbeth, "O sleep, O gentle sleep, nature's soft nurse, how have I frighted thee?" And then we move to another Elizabethan, Thomas Dekker. Sleep is the golden chain that ties health and our bodies together. They knew way back in the 1600s how important sleep was. And yet, in the industrial age, particularly during the 20th century, sleep was completely marginalized. So here we have Thomas Edison, the inventor of the electric light bulb, and of course part of the reason why we have been able to ignore sleep. We've overridden sleep by changing our light environment. And Edison famously said, "Sleep is a criminal waste of time and a heritage from our cave days." So different from the way that Shakespeare and the Elizabethans were thinking about sleep. Perhaps the low point in our regard for sleep was in the 1980s, and I think beautifully illustrated by the film Wall Street. And some wonderful phrases from that film. "If you need a friend, get a dog," which I think is a little harsh. Another one, which is pertinent to our present day times. "The point is, ladies and gentlemen, that greed, for lack of a better word, is good." And sleep was also stacked up with these phrases. "Money never sleeps." Implication being, if you sleep, you're missing out on opportunities for growth. In fact, I think Margaret Thatcher famously said in the 1980s, "Sleep is for wimps." Now, we've come back from that. It's not quite as bad as those attitudes are changing. And those attitudes are changing because, ta-da, of research in the neurosciences. We're beginning to understand why sleep is so very important to us. And I won't go into lots of details, but just to flag up some of the exciting areas of where neuroscience is showing how important sleep is for normal bodily functions. One idea, and one very clear explanation for why sleep is so important, is that we sleep for cellular restoration. Sleep is a process that allows the repair and replacement of key components of our brain and our body. And actually, this idea has been around since the time of Aristotle. I mean, he thought that sleep was essentially for repair. But it's become very popular recently because it's been shown that certain genes associated with repair and replacement are only turned on during the processes of sleep. So yes, I'm very happy. I think cellular restoration is part of the reason why we sleep. I'm less convinced by energy conservation. Essentially, we sleep to save calories. Now, when you actually do the sums, and you look at how many calories you burn while you're asleep versus when you're just sitting quietly, it's about 110 calories at night, asleep versus just sitting quietly. So 110 calories is about the equivalent of a hot dog bun. And I have to say, for such a demanding 36% of our lives for a hot dog bun doesn't really make a huge amount of sense to me. So I'm less convinced by this. Where we have amazing data is in brain function. Sleep has evolved for brain performance, learning and memory. If we don't sleep, our capacity to memorize events is completely smashed. But it's not just our ability to take information in and store it. Some beautiful data has shown that if you want to come up with innovative, novel solutions to complex problems, then a night of sleep can have a huge impact. It can increase, you can go from essentially a 20% capacity to come up with new ideas to a 70% after a night of sleep. And that's because of really some of the exciting and interesting things going on in the brain during sleep. So, neuroscience has begun to, I think, reverse that trend, perhaps started by people like Thomas Edison and its low point during the 1980s. Sleep is very important for lots of reasons. Okay, everybody comfortable? Any quick questions? All happy? Because what I want to consider next then is how we actually generate those 24-hour rhythms. And for that, of course, we need to go into the brain. Here's a cartoon of the brain, and here's the eye. And if we flip the brain on its back, and you see the optic nerves going into the brain, here's the pituitary gland, they fuse. This bit here is called the optic chiasm. And if we look just underneath that, through this slice of the brain, here we see two structures. They're called the suprachiasmatic nuclei. And that's the origin of that day within we've been talking about, those 24-hour oscillations. We see here illustrated, this is a real SCN. These individual cells are in yellow, and the projections from those cells are in red. And what's turned out to be absolutely amazing is that if you take one of those cells out and stick it in a dish, you can still see 24-hour oscillations in electrical activity of that single neuron. So, individual cells within this master clock here can generate a 24-hour oscillation. And there's about 50,000 in the human brain, and they all work together to give us this internal clock. Now, the fact that one cell can produce this 24-hour rhythm tells us something really important about how this 24-hour rhythm is actually generated. The 24-hour rhythm cannot then be the product of cell-cell interactions, but it must be a subcellular mechanism. There must be a molecular basis to this clock. And in fact, our understanding of the molecular clock really starts with work on the fruit fly from the 1970s. Genes were identified in the fruit fly, which gave this animal its 24-hour rhythms. Then with the sequencing of the human genomes and other genomes, like in mice, the same genes were turning up. And when these genes turned up, they thought, well, maybe they're doing the same thing in us and other mammals as they are in the fly. So these genes were then mutated, put into a mouse, and the mouse had a completely disrupted 24-hour rhythm. So what's truly extraordinary is that species separated by what? 600 million years are, broadly speaking, building those molecular clocks in the same way. Huge conservation of the molecular clocks across the whole of the animal world. So very ancient, probably, in terms of our evolution. How does molecular clock work? Well, you can think of it as basically a feedback loop. And let me explain what I mean. There's a whole bunch of clock genes. In fact, at the latest count, you'd probably say there were 12 to 14, maybe 18, depends on who you talk to, genes that are critically important in the development of this internal rhythm. What happens is that these genes are turned on, and they produce a message which produces a whole bunch of clock proteins. These clock proteins then work together, go into the nucleus, and actually turn off their own genes. So no more message, no more protein, and then these proteins are then degraded, and then the whole thing can start again. So what you've got is essentially a cycle of protein production and degradation, and it's that cycle that gives the signal that drives all of that biology that we were talking about earlier. And what's turning out to be really exciting is that changes in these genes are being linked to whether you're a morning or an evening type. And let me explain what I mean by that. Here's the ideal normal sleep pattern. Very few people actually sleep like this, as it turns out. What we've got here, each line represents a day, and we see here that they're asleep. They're going to sleep at around about 11 o'clock. Weekends, they're going to bed a bit later. Work days, the alarm clock is forcing them out of bed, but it's a fairly stable rhythm. However, there are individuals who have massively delayed sleep or massively advanced sleep. And there's a condition called familial advanced sleep phase syndrome. Those poor individuals have to go to bed around about 7:30 in the evening. They're just shattered. They just fall asleep. And then they're waking up at around about 4:30 in the morning. Their whole biological clock, their whole molecular loop has been advanced through time. And in that particular condition, advanced sleep phase syndrome, it's a defect in a single change in one of these proteins, of these proteins that form the molecular clock, that has speeded up the clock. So we're beginning to get a real sense of the molecular basis of whether you're a morning type or an evening type. And as we'll see, but it's more than just genetics. When we start talking about teenagers, there's also developmental changes that are going on as well. So there's both genetics and developmental changes. Oh yes, this is, anybody recognize this chap? Benjamin Franklin. Benjamin Franklin famously said, "Early to bed, early to rise makes a man healthy, wealthy, and wise." Well, let me tell you, there is no evidence whatsoever that you have a better job, you earn more, you're more intelligent if you get up early and go to bed early. The only experience I think I've found from morning people is that they're just horribly smug. Okay. So, what I've said is that there's this clock ticking away in the base of the brain. And I haven't talked about the details, but I will in a moment, is that this clock, this molecular oscillation, is set to the external world by exposure to the light-dark cycle detected by the eye. And then what I've sort of implied is that this clock drives those 24-hour rhythms in physiology and behavior. And that's what we thought for years. There was some message from the clock which essentially forced rhythmicity in muscles, gut, liver, lungs, brain, whatever. But we got it wrong. What was discovered is that essentially every cell in the body, in isolation, has its own little clock. So there are billions and billions of clocks throughout the entire body, skin, liver, gut, whatever. And so what seems to be happening is that the SCN acts as a bit like the conductor of an orchestra. It's producing a rhythmic signal from which the rest of the orchestra takes its reference cue and aligns its rhythmic biology accordingly. If you shoot the conductor, you destroy this part of the brain, then everything starts to become misaligned and smear and breaks down. And so instead of sort of a beautiful symphony, you have just a cacophony of noise. So that's what's going on. It's not forcing rhythmicity, but it's coordinating rhythmicity in the rest of the physiology of the body. Okay. But I also want to talk about sleep. And sleep is so much more than just this body clock. Let's look at sleep in some detail. Here's the sleep-wake cycle, rest, activity. And of course, the body clock is critical in timing the sleep-wake cycle. Now is the appropriate time to be awake, now is the appropriate time to be asleep. But there's another really important oscillator, and it's the intuitive part about sleep, and it's called the homeostat. And what that means is, the longer you've been awake, the greater the sleep pressure, the greater the need for sleep. And what tends to happen is that, and when you sleep, of course, the pressure drives back. So what's happening, from the moment you wake up, the sleep pressure is building up and up and up. But you don't fall asleep because the clock is saying, keep awake, keep awake, keep awake. It's only 11 o'clock or so at night when the clock then says, okay, now is a good time to be asleep, that the sleep pressure kicks in and then you fall asleep. So you've got these two really important oscillators. Now, what is this homeostat? We don't really know, but we think that a substance called adenosine might be really important, a buildup of adenosine within the brain. And it's really interesting because coffee actually blocks adenosine receptors in the brain. So the reason why coffee works and keeps you alert is because it's interacting with the homeostat. In humans, of course, there's a third. Oh yes, and I should say that the sleep-wake cycle, of course, feeds back on the homeostat. So if you sleep, then the pressure is driven back. That's why a nap in the afternoon will delay your sleep at night, because you've driven back the sleep pressure. In humans, of course, there's this other factor, which is social timing, the alarm clock. The alarm clock, of course, is the thing that gets most of us out of bed in the morning. And, of course, the sleep-wake cycle feeds back on our social timing. So you have this important set of interactions. The sleep-wake cycle, as we'll see later, has a massive impact upon our mood, our ability to function, and indeed our mental health, and these, in turn, feed back upon the nature of the sleep-wake, the quality of the sleep-wake that we get. Now, the really important thing I want to stress is that we've talked about the SCN, and that's one bit of the brain. But to generate all of this, you need lots and lots of bits of the brain interacting. So we have here the basal forebrain. This is the hypothalamus. There are at least 4 key structures in the hypothalamus: the master clock, the SCN, the lateral hypothalamus, the ventrolateral preoptic nuclei, the tubral mammillary nuclei, all interacting and then feeding down into this ancient bit of the brain. Here's the spinal cord, and this is the base of the brain, and there are multiple structures all down here. And what happens is that this lot interact and then feed forward and bathes the brain in a whole raft of neurotransmitters that essentially keeps us awake or turns off and drives us into the sleep state. So there's masses going on. There's not a single structure regulating sleep, but lots and lots of them. And we'll come back to this point later. Oh yes, and these are all the neurotransmitters. So glutamate, GABA, ghrelin, orexin, noradrenaline, histamine. Histamine, really interesting. Histamine, of course, is one of those neurotransmitters that keeps you awake. So if you take those drowsy antihistamines, what you're doing is blocking the receptors that would normally keep you awake. In fact, lots of people use antihistamines as a way of self-medicating to try and get themselves off to sleep. Not a smart thing to do. So there's lots of variability about how susceptible you are to the impact of these various drugs. Serotonin, acetylcholine, masses and masses of stuff going on. Almost all the brain neurotransmitters are at some level involved in sleep. And again, we'll come back to this because all this complexity makes sleep-wake a very vulnerable behavior to disruption. And again, we'll come back to that important point later. Okay, everybody happy? We've talked about 24-hour rhythms, how they're generated within the brain. Before we go on about light regulation, any burning questions? Yes?
It's very specific, sorry. The piece that you showed, the accident, is the car accident?
Yeah.
And the way they peaked at that certain time?
Yes.
You don't know how many of those accidents... Sorry, how many of those accidents were caused by people who had been up from the previous day versus people who had woken up in the middle of the night and gone out to drive?
Yeah, I'm going to talk about car accidents in a bit more detail later. But what's happened with those studies that people have been interviewed afterwards, because they've had an accident and therefore they're interviewed by the police, and so we've got pretty reasonable records, and a lot of it is not associated with fatigue. Of course, fatigue is worse. If you stay up and up and up, you're much more likely. But a lot of it is just simply falling asleep at the wheel under normal circumstances. They haven't been up all night, so it's not simply fatigue. It's that internally driven rhythm. It's a really good question. Okay, let's talk about the eye, light, and time. So, eye regulates the clock. Clock produces a beautiful rhythmic activity. And what I've depicted here is what's called an actogram. We see days plotted along this axis. When the individual's awake, it's a thickened portion of the line. When they're asleep, it's a thin portion of the line. And we'll see sort of patterns like this later on. And I just wanted to recap before we move forward. If we have no clock, if that region of the brain is destroyed as a result of a tumor, and in fact, we've been working on it. It's a very interesting story. A very good friend of mine in college came up to me and said, my husband's got a brain tumor, and I think his 24-hour rhythms are beginning to fall apart, and he wants you to study him. It's very interesting. So we did. A PhD student studied him for the last, basically, 10 months of his life. And what was so tragic is as the tumor advanced through this region of the brain and destroyed this part of the brain, he went from a 24-hour pattern of rhythmicity to essentially arrhythmicity entirely. It's quite extraordinary. It's the first actually clear documentation in humans. We've got lots of animal models of that. And it's so interesting because he then became fascinated by this. He's a scientist, and so he felt that he was actually contributing to science in some way because of this ferocious and unkind disease. Okay, so that's what happens if you don't have an SCN. But what happens if you don't have an eye? If you've got no eyes, then you can't detect this light-dark cycle. But the clock keeps on ticking away. But it can no longer be regulated by the external world. And so what we see is that activity or rest activity starts to get later and later and later each day. Humans tend to have a body clock that's slightly longer than 24 hours. And so that's the sort of pattern that we would see, dim, dark cave, constant light, constant temperature, or if we had experienced some appalling, ghastly accident and we had no eyes. But let's just think about what the eye is being expected to do here. And this goes back to some of the work that we started, I suppose almost, 15, maybe even 20 years ago. Because something was really puzzling me. Here's the eye, and of course the familiar function of the eye, I need hardly mention this, is to detect an image of the world. That's what we've understood. We've understood that the eye does this, and we've studied the eye seriously for 150 years. But the task of image detection is completely different from the sort of light information you need to regulate the clock. If you think about it, what the clock needs is brightness detection. It needs to assess how much light there is in the environment over relatively long periods of time, because that tells it roughly what time of day it is. And it's that overall levels of brightness that set the clock. Now these, image detection and brightness detection, are entirely different. And it was really difficult for me to understand how one eye, one structure, could extract these very different sorts of sensory information. Just think about it. I mean, the reason we can detect an image is because as soon as we've seen the light, essentially we forget we've seen it instantly. Because if we didn't, then as we moved around, life would just be a complete blur, a complete smear. And of course, this on-off response in image detection is the last thing you need to get reliable judgments of the amount of light in the environment. So, as I say, 15, 20 years ago, we started to think, how the hell can the eye actually do this? Here's a classic sort of view of the eye. We've taken a slice here, and here's the photoreceptor cells, the light-detecting cells, the rods and cones, which of course give us our image of the world. The rods, dim light vision, black and white vision, and then the cones working together to give us this extraordinary sense of color. Then we go to the next layer within the eye, which are the horizontal cells, the bipolar cells, and the amacrine cells. And these take information from the rods and cones and give us our first processing of image detection before messages are assembled and sent by these ganglion cells, and these cells form the optic nerve, into the brain, and the brain then starts to construct an image of the world. And the big question was, how can these cells generate brightness detection? How can it do it? And so we started by working on mice. Mice with genetic diseases, naturally occurring genetic diseases, whereby these animals had lost most of their rods and cones and were left with a few cones in a pretty grim condition. The important point was these mice had no capacity to detect an image of their world. They were visually blind. And we then decided to see how they would regulate their clock in response to light. And so we popped them in a running wheel, attached it to a computer, and we were asking a very straightforward question. If those degenerate eyes can still regulate the body clock, then under a light-dark cycle, remember these are nocturnal animals, they'll be active during the dark and they'll be asleep during the light phase. If those rods and cones are important for regulating this, then we would see the fact that their active and sleep phase would drift through time. Is everybody happy about what we're doing? So, what did we actually see? We saw this, which is really exciting. So these mice, these blind mice, sorry, 3 blind mice, that was awful, could regulate their body clocks in response to light. So the first really important observation was these mice are visually blind but not clock blind. And that was remarkable. And of course, this was 15, 20 years ago, so I was young and I suppose a bit pushy. And so we then said, okay, well, maybe there's another light sensor within the eye. There's something else. It's not just the rods and cones. There's something else that's regulating this biological clock. And the response of the vision community 15, 20 years ago, and in fact, I would say up until 5 years ago, is summarized in the next slide. I kid you not. It was absolutely ferocious. I showed those early data at a scientific meeting, and got to the stage, well, maybe there's another receptor in the eye. And somebody at the back stood up, said, bullshit, and actually walked out. It was really nasty. And the arguments were along two lines. We've been studying the eye for 150 years. Are you seriously telling us that we've missed an entire class of photoreceptor within the eye? And as I said, I was young, so I said, yes, you're wrong, and I'm right. A more serious criticism was the circadian system can probably maintain normal photosensitivity with just a few rods and cones. Your model just isn't very good, because remember, there were a few degenerate cones left in those animal models. So, of course, what that drove us to do was better experiments. And they were quite right to criticize us, because we hadn't done the definitive experiment. We then used genetic engineering to completely remove all of the rods and cones from this mouse. We called it the RDCL mouse, and to our undiluted, intense pleasure, they could regulate their clock absolutely normally. Now, let me stress, if you stop light getting to the eyes with opaque contact lenses, then this capacity to regulate the clock was entirely gone. So it's definitely something in the eye. And the big question there, oh yes, and then of course, this was mice. What about humans? And we were very fortunate to work with an incredible lady who had lost her rods and cones as a result of actually still a genetic disease which we don't fully understand. She had no rods and cones. Her retina looked like this. It's absolutely appalling. No conscious light detection whatsoever. And yet her biological clock was beautifully aligned to the light-dark cycle. She was just like our genetically engineered mice. So we had from two different sources, mouse models and humans, the fact that in the absence of the rods and cones, you could regulate your clock. So what was it? What was the extra cell in here? And we now know that it's a photosensitive retinal ganglion cell. Those ganglion cells, which form the optic nerve, about 1 in 100 of those cells is directly light sensitive using a special light sensitive molecule, and they go in, detect brightness information, and set the clock to local time. Now, this is what those cells look like. They're so beautiful. Of course, I'm biased. This is just one. Here's the cell body and all their little photosensitive processes. And what they do, that's at high power, this is at lower power, is they form this sort of photosensitive net that entirely encompasses the eye. So as light comes in, they detect this light, this brightness, and then fire that off into the master clock within the brain. Now, there's some very serious clinical implications for this, and that's why I chair a department of ophthalmology in Oxford. Because visual blindness need not result in the loss of all light detection by the eye. However, if you think about it, sleep and 24-hour rhythms are almost ignored entirely in clinical ophthalmology. Nobody actually asks you about your sleep. So what I've been doing is working closely with my clinical colleagues in the Oxford Eye Hospital, particularly Susie Downs, who's a consultant there, and we've been asking the question, what is the impact of ocular disease on human sleep-wake biology? So all the patients coming through give us some assessment of their sleep-wake capabilities. And I won't give you all the data, but I'll just summarize what's going on. So there are, of course, lots of diseases which result in major loss of the rods and cones, such as diabetic retinopathy, Leber's congenital amaurosis, choroideremia, and these individuals are visually blind. But of course, these photosensitive ganglion cells are still there. So under these circumstances, if you've got these photosensitive ganglion cells, people must be told, expose yourself to sufficient daytime light so you are able to lock your body clock on to the light-dark cycle. And in fact, unless there's really good clinical reasons, don't cover up your eyes with dark glasses. The reason why most people are encouraged to cover up their eyes with dark glasses is because their eyes don't look very nice. There's no good clinical reason for it, usually. It gets even more terrifying because there has been a tendency to say, well, you know, your eyes are now no good to you. You've got this disease, you're blind. The eye is a source of infection. You can't see to look after it. I tell you what, let's make your life so much simpler by popping in one of these, or two of these. And so the eyes are removed, and they're replaced by a glass eye. And then, of course, completely unwittingly, people will be plunged into a world of unremitting jet lag, effectively, for the rest of their lives. And so what we've got to do is stop this. And that's what's going on now in Oxford, trying to produce the appropriate guidelines about when you should and should not remove the eye. In the same way, of course, there are diseases which don't affect the rods and cones, but you've lost this bit of the retina. So you've lost any visual information, but also any light information about setting the clock. But all is not lost because there's, such as acute glaucoma, because these individuals can now benefit from conditions which consolidate sleep. So many of you may have heard of the substance melatonin. If you take melatonin, 3 milligrams of melatonin, 11 o'clock at night, you can take that drifting rhythm and set it, and you can essentially replace light with this biological marker of the dark. So all is not lost. The point I'm trying to make is that the clinical diagnosis of complete blindness must assess the state of both the visual system and these photosensitive ganglion cells. And in most departments of ophthalmology around the world, that is simply not being done. Eye loss plunges individuals into a world that lacks both vision and a proper sense of time. There's two functions that the eye is performing. And clinical advice in ophthalmology must incorporate the impact of eye diseases on sleep and circadian entrainment. I mean, I've made the life of my clinical colleagues twice as difficult. They've not only got to think about vision, but they've now got to think about this whole new area of body clocks and sleep. But the numbers of individuals worldwide is truly extraordinary. There are 39 million people worldwide who are completely blind, 285 million who are severely visually impaired, and then 246 million with low vision. That's 500 million people worldwide. And the extent to which a knowledge of these new receptors might hugely inform and improve their quality of life, I think is a really important issue, and an area where basic science is now informing clinical practice. Okay, let's now move on to another topic, which is shift work in teenagers, and we're going to start with teenagers. So here's our idealized plan. As I say, very few people are actually like this. You've got days here, here's the light-dark cycle. People are basically going to bed at 11 o'clock, and they're sleeping for about 8 hours. The alarm clock is getting them out of bed at 7 o'clock in the morning. They have some sort of social life, so maybe on a Friday night, they'll stay up a bit later on a Saturday night, and of course have a slightly delayed sleep on a Sunday night. But that's the idealized pattern. Stable, nice sleep. The elderly is rather different. There's a tendency to go to bed earlier, but you often wake up, and usually you're waking up pretty early in the morning, and there's various naps going on in the day. Now, what's really important is that we have very little idea why that sleep pattern starts to break down in the elderly. Really very little neuroscience, very little research has been done. So this is an area, I think, of very important research in the future. But let's go to reduced and fragmented sleep. But let's now look at the teenager. And we have one teenager, any more than one teenager in the audience, so we might have to ask you about whether this is what's going on with you. So there's a tendency to go to bed really late. And at the weekends, go to bed really, really late. And then often, after you get home from school, have a sleep. So what you find in teenagers is great delayed and reduced sleep. So we see a delayed body clock. It's really very interesting. It seems that the hormonal changes that are going on at the beginning and throughout puberty, and we don't understand it fully, make the clock later. So there's a genuine biological predisposition to go to bed late and get up late in teenagers. And so all the rhythms that we were talking about earlier, they are all delayed in teenagers. And let's look at alertness in some specific detail. So here's a zooming in of this. Here's an adult. And so we said that alertness begins to crank up in anticipation of activity. And in most adults, we're fully alert by around about 10 o'clock in the morning. Peak levels of alertness. So in many teenagers, that's going to be delayed by at least 2 hours. So they're not fully alert until 12 o'clock. And in about 10 to 20% of teenagers, they're delayed by 4 hours. So they're not fully alert until around about 2 o'clock in the afternoon. This is real. And so what are the implications of that delayed alertness coupled with reduced sleep. Because there's not only that biological tendency to go to bed late and get up late, but also there's all this stuff going on. There's gaming and texting and watching television until the early hours. So you've got two really difficult things. There's biology and also the fact that the teenage bedroom is a dodgy place. There's lots of naughty stuff going on, which is further delaying nighttime sleep. And I'm not going to embarrass this young gentleman at the front and ask him what his bedroom is like. Mary Caskadon at Brown University in the States suggests that US teenagers are getting about 7.5 hours of sleep, but as many as 25% are getting 6.5 hours. What do they need? She estimates from lab studies that for fully cognitive behavior, a teenager needs 9 hours of sleep every night to be fully functional at school. So does all this matter? Well, these are some experiments by some colleagues in University of Toronto. And what they did was look at the correct answers to a whole bunch of tests. They compared teenagers and their teachers, who are adults, mid-morning to mid-afternoon. The teenagers from mid-morning to mid-afternoon increased their scores by 10%. That's huge. The teachers, the adults, however, went in exactly the opposite direction. And that's a huge problem, because when I've talked about this stuff before, there's probably some teachers in the audience now who are looking at me savagely, because they say, how dare you? You're an academic, you're in the ivory towers, you don't know what it's like to teach. I do. And I know that the morning is the best time to teach demanding subjects like mathematics and things like that. And of course, there's a real imbalance here, because the adult is feeling bright and fresh, coming in, able to teach. The kids are half asleep, so they're sitting there quietly. By mid-afternoon, the kids are bouncing off the walls, and the teachers are vaguely sedated. So there's a really difference in our biological clocks. Okay, so what happens when you have a later start day to the school, coupled with this whole idea about sleep hygiene? And so I worked with headmaster Paul Kelly at a school called Monk's Eton in Newcastle. And in 2010, they were starting their lessons at 8:50 in the morning. And then they switched to 2011 to 10 o'clock. And you see what this axis shows is the percentage of students getting the minimum requirements that the government would expect a school to get. So 35% of these kids were getting the minimum requirements with an 8:50 start. That jumped to 53% and was sustained over the following year. So a massive difference. The national average in the UK is there. So this is a school that has certain social issues, and so they're not even reaching the national average. But you see a big effect of this later start time. The more dramatic data was from those kids who are socially disadvantaged. 12% were getting the minimum requirements set by the government with an 8:50 start, and that jumped to 42% after the later starting day. And actually then went above the national average under those circumstances. So a later starting time is very important. But, and I must stress, it has to be coupled with good sleep hygiene. What do I mean by that? Well, if you're interested in this, I wrote a short article in New Scientist on the 22nd of April. And what we try to address in that article is, well, how do you know if you're getting enough sleep? Well, it's really obvious. If you're dependent upon an alarm clock or your parent to get you out of bed, you're not getting enough sleep. Ideally, you should wake naturally. If you take a long time to wake up, so the alarm clock's gone off, your mum or dad or whoever has woken you up and you're lying there thinking, I just can't get out of bed. If you feel sleepy and irritable during the day, and if you're really doing stupid and impulsive things, you're just not getting enough sleep. What do you need to do? Well, the bedroom, as I said, teenage bedrooms are dodgy. The bedroom must be dark and it mustn't be too warm. It's quite important. Overheated bedrooms are really bad. Don't text, don't watch TV, use computers for at least half an hour before you go to bed. Also avoid bright lights before you go to bed. What's the last thing that most of us do before we go to bed? We go into a brightly lit bathroom and we brush our teeth with always bright light. And of course, bright light increases levels of alertness and actually delays. So if you can, hopefully I'm going to change all of your behavior now. Every night from now on, you're going to actually dim the lights and clean your teeth under as dim a light as you possibly can. So start to wind down for sleep. Don't try not to nap during the day, because as you talk, that sleep pressure, you'll actually delay the time you can get to sleep at night. Seek out natural light, particularly in the morning, because that brings the body clock earlier in time. And critically, avoid those caffeinated drinks after lunch. Some people are incredibly sensitive to caffeine, and caffeine can stay in the body. Its half-life is between 5 and 9 hours. So if you take a cup of coffee in the middle of the afternoon, you will, for most of you, delay sleep at night. It's quite remarkable, actually. After oil, coffee beans are the highest traded commodity on the open market. And I think it's amazing. With our increasingly 24/7 society, what's the shops that have just blossomed? Well, of course, Starbucks and Costa. Maybe that's part of the thing that's fueling our need for caffeinated drinks is this sleep. Okay, so we talked about the teenager, but I also wanted to just touch upon the shift worker. A different set of problems here. Sorry, before we go on, any questions about teenagers and their sleep? Yes, lady at the back. I think there's a microphone.
Oh, sorry. You're talking about coffee, alcohol.
Yeah, I'll come on to that. Absolutely. Yes, brilliant. Thank you. And what I didn't say, I mean, I don't mean to trivialize this stuff. I mean, in fact, I worked with a Channel 4 television program on a school in Liverpool about sleep. And I interviewed a 13-year-old young lady. And I said, what's the sleep like? And she said, oh, it's fine, it's great. I said, brilliant. So why is that, do you think? What are you doing? She said, well, I'm taking my mother's sleeping tablets. 13-year-old. And I said, okay, and so what are you doing? You know, you're feeling a bit tired the next day. She said, well, I can get over that because I've usually had about 3 Red Bulls before lunchtime. Here's a developing plastic brain, and it's being assaulted with these stimulants. So we will talk about this more. I mean, I found this really tragic because these teachers are phenomenal. They were coming in during half term to give these kids extra classes, dedicated. They had every facility they needed, and they were saying that for the first 3-4 hours, kids are falling asleep in class. So all of this, support, all of the things that without any knowledge of the importance of sleep, they're just essentially squandering this educational opportunity. Any other quick question? Yes, question down here. There's a microphone that we could get.
Great, thank you. You were talking about it mainly being through the eye that you set your master clock and everything else follows that beat. Yeah. You know, when they were talking about jet lag, I think about 5-6 years ago, it was, the back of your knees was one of the most sensitive places that you could have.
Yes.
So,
do you know, I'm so angry I can barely speak. So at the time we were doing, those people actually misrepresented our work because they say, Foster's shown that, you can be blind and you can still regulate your body clocks. Therefore, light behind the knee. Then what they didn't say is if you didn't have an eye, you couldn't regulate your body clock. And in fact, there's lots of dirty secrets have come out about this whole thing. Not least that when they were having their knees illuminated, they were going around watching television. The controls were really bad. And I'm on camera, so I won't, but over maybe a glass of wine or something later, we can dish the dirt. But there's some, and so a group of colleagues at Harvard tried to repeat the experiments completely using the same methodology, but better designed. Absolutely no effect. I mean, it was really interesting though, because Philips Lighting were taking patents out. Airline seats were being designed with little lights behind the knees, and it was one of those things where and it was a paper published in one of the top journals. It was absolute crap. I mean, it was extraordinary, and in fact, it was really bad for us because we had some grants in, and saying. They were rejected. And they said, well, why is Foster looking for a new receptor within the eye when we know there are receptors behind the knee? Sorry, I should calm down. It was a difficult time. Okay, bearing in matter of the time, we should probably move on to shift work. I won't spend too much time on shift work. I just want to really emphasize what's going on here. You can be on the night shift for 20 years, but the body clock does not shift with the demands of working at night. So if you think about it, the night shift worker has to be active when the body is saying, now is the time for sleep. So what you can't possibly expect is peak performance, and you'll see some of the consequences of this. But the other huge problem the night shift worker faces is that when they're trying to sleep during the day, the body clock is saying, no, it's daytime, you should be awake. So many night shift workers are getting I think, less than 5.5 hours out of every 24. Now, if you did that to a political prisoner, you'd be up in front of the the International Tribunal at The Hague. It would be torture. And yet, perhaps as much as 20% of our working population are suffering as a result of night shift work. Now, I do have a question for you. Why do night shift workers not shift? If you fly to New York or across the Atlantic or whatever, you do lock onto local time. So why don't night shift workers shift? Somebody said, natural light, exactly. So what's happening, of course, is that they're under relatively dim light in the factory or in the office. And then they're experiencing bright natural light on the journey home or on the journey in. And the clock always defers to the brighter light signal as being daytime. And so if you take a night shift worker and you increase the amount of light in the factory and you hide them from natural light during the day, they will adapt. But most night shift workers never do adapt. So they're having to override this body clock saying now is the time for sleep. And what I want to move on to, oh yes, I found this recently. So this is brilliant. This was tips for married shift workers. This was put on a notice board, and this is what was scrawled underneath it. Don't work night shifts. which I thought was absolutely fantastic. Don't work shift work. Okay, what I want to do now is really talk about the serious health consequences of sleep and circadian rhythm disruption. This is the term that we've come up with, a sort of we've called it SCARD. It sounds a bit like a Bond villain, doesn't it? SCARD. And it's a sort of a shorthand. And I just want to go through some of the consequences of shift work problems, teenager problems, anybody who's really getting disrupted or reduced sleep. Now, some chilling statistics. Some of these classic accidents have been associated with shift work. In the USA, 100,000 crashes every year are related to sleepiness. I think the lady was up here was asking this question. The crashes happen, the sleep history of the people are taken into account, and it's 100,000 crashes every year on the US roads. Exxon Valdez. It's always assumed that this went aground because the captain was drunk. Actually, he was drunk. He was in his cabin asleep. And what was happening is that it was the people driving this boat were hugely fatigued. And the investigation determined that fatigue was a factor in the crash, and the Exxon Shipping Company was criticized for failing to provide a rested crew. Huge implication of the Exxon Valdez. This Air India Express crash, accident investigators said that the pilot could be heard snoring in the cockpit voice just before this disastrous, crippling landing. And of course, in 1986, we had Chernobyl, and the International Nuclear Safety Group determined that human error related to sleep deprivation was a factor in the accident. Apparently what was going on is that these people were hugely sleep deprived. And of course, when you are sleep deprived, you become more impulsive. You can't actually be reflective about the sorts of things that are going on. And they're saying, oh, why don't we try this with the actor? Why don't we do that? And of course, it just got out of hand, and it was a whole bunch of sort of sleep deprived, impulsive individuals, which caused this appalling disaster. The problem is, tired brains, as we've already touched on, when the alarm clock goes off, you get caffeine, and if you're a really naughty, tired brain, nicotine. Nicotine is extremely effective in keeping you awake. And then, of course, as I think the lady back here, what about alcohol? And of course, you're wired. The whole day is that you're wired. And then, of course, these substances can last, particularly caffeine, in the body a long time. So then what do? Well, you think, I've got to be up in 8 hours or 6 hours or whatever it is. I tell you what, I'll just take a few sleeping tablets, or I'll take some alcohol and I'll sedate myself. And of course, you will induce sleep, but it's sedation. It's not biological sleep. So many of the advantages that you get in a sleeping brain, ability to come up with novel solutions to complex problems, all those sorts of things are completely smashed by alcohol and sleeping tablets. So you need alarm clock, more stimulants, more sedatives, and so much of the Western world is locked into this appalling stimulant-sedative feedback loop, not least our teenagers. And that's, I think, really alarming. There's a very important relationship between our digestive system and our brain in the determination of appetite. What normally happens is that the hormone ghrelin reaches the brain and promotes consumption of food. And when you're full, leptin is released, which reduces appetite. And so under normal circumstances, this seesaw of weight gain and weight loss is about balanced. But then you kick in with sleep loss, sleep and circadian rhythm disruption. This hugely distorts the seesaw to produce ghrelin. So a wonderful study that was undertaken by workers in the United States. They took healthy young males, and one group were allowed to sleep 4 hours a night, and the other group up to 10 hours if they wanted. After 7 days, healthy young males, only 7 days, ghrelin was up by 28%, their carbohydrate consumption had gone up by 35 to 40%, and their ability to clear glucose from the circulation was bordering on the diabetic. So there's a very important relationship between sleep disruption and appetite. No great surprise, shift workers tend to have a predisposition for weight gain. Stress. Of course, we'll all be familiar with this axis. Stress impinges upon the brain and ultimately the release of the stress hormone cortisol. Now, acute stress is very valuable. It gets us in, it's the fight or flight response. It gets us out of dodgy situations. But sustained activation of the stress axis is bad, and that's what's happening under conditions of sleep and circadian rhythm disruption. What's going on? Well, of course, when you're stressed, you're throwing glucose into the circulation. High level of glucose all the time make you glucose intolerant and insulin resistant, and so diabetes 2 is very common in night shift workers and in those individuals who are not getting enough sleep. Gastric acid secretion as a result of the stress increases. So ulcers, much more common in night shift workers compared to day shift workers, particularly taxi drivers. Very interesting, that one. I should add, I mean, one of the great problems of being on the night shift is that your digestive system is in the shutdown state. So what do we give our night shift workers to eat? High fatty food, high glucose food, can't really digest it. It's the worst possible thing you could be giving him. Sustained levels of cortisol, one of the things we do know is high levels of stress suppress the immune system, which may be the reason why you get higher rates of cancer and infection in night shift workers. Blood pressure, cardiovascular disease, much greater in night shift workers compared to the day shift workers. And after long-term stress, you even get impaired memory formation, cognitive decline. So, cognitive and memory impairment, substance abuse, metabolic problems, cardiovascular problems, and immunity. That's all some of the well-documented impact of sleep and circadian rhythm disruption. Which takes me to my last topic, and I promise I'm almost done, which is mental illness. This, I think, is an absolutely fascinating new area and perhaps rather unexpected relationship with these bits of the brain. We've known since the 1880s, here's Emil Kraepelin, the father of psychiatry, who was talking about abnormal patterns of sleep in conditions that we now call schizophrenia. So we've known about this, well documented, from the 1880s. And indeed from diary data. Vincent van Gogh classically said, I often think that the night is more alive and more richly colored than the day. And of course he was deeply disturbed in many respects. And in his diary, I put my heart and my soul into my work and I've lost my mind in the process. I mean, really tragic. So hugely disrupted sleep, well documented in mental illness for a very long time. And yet, we get to the 1970s, this sleep disruption thing in conditions like schizophrenia was simply viewed as a byproduct of the introduction of antipsychotic medicines in the 1970s, and then they just said, oh, well, it must be the antipsychotics, ignoring the fact for 100 years before that, sleep disruption had been talked about, way before the introduction of antipsychotics. And if it wasn't the antipsychotics, the argument was, well, the abnormal sleep in things like schizophrenia is basically because they don't have a job. And this is a real quote this is why I got into this whole area, from a psychiatrist I was speaking to in a lift. My patients can't hold down a job, so no wonder they get up late, miss my clinic, and don't have friends. Quite extraordinary to me. So that prompted us to start to work in this area. What had been thought about, the model that people had thought about, is that, okay, psychiatric stress is associated with sleep disruption. And whenever it was thought about, and it was very barely addressed, it was, well, the relationship is probably due to social isolation, there's no social constraints, or the fact that they're on drugs. And that was it. So what we decided to do was to look at sleep-wake disruption in schizophrenia in detail. Now, this is one of those patterns again. It's slightly differently plotted. So here's when the person was active, here's midnight, and what we've done is we've given 2 days of data, which means you can see the patterns more clearly. So essentially day one, day 2, day 2. It just see this as midnight. And we see, even in the unemployed, a very nice rest activity, but going to bed a little bit later than perhaps the average individual, but really a perfectly normal, stable environment. Every patient with schizophrenia we've looked at has been disrupted. This is perhaps the mildest example, where lots of activity is going on after midnight. This individual just drifted through time, and I'll show you this individual again in a moment. Huge amounts of activity, and in fact, there's vaguely stable, but then falls apart completely. Look at this. I mean, just going worse and worse. And in this individual, no 24-hour pattern at all. It's as if their clock was smashed. So appalling, deeply severe rest activity. Here's one person we've started to follow from 2001. And she had delayed patterns, and then she'd break away. And then she'd drift. She'd get up later and later and later each day. In fact, she spent the whole of 2004 drifting endlessly through time. Not only do you get this appalling scarred sleep and circadian rhythm disruption, but also hugely poor comorbid health issues. Impaired cognition and memory, increased substance abuse, metabolic abnormalities, cardiovascular disease, reduced immunity. Where have we seen that before? Well, of course, the impact of SCARD, impact of sleep. People know about this poor health in patients with mental illness, but they never link it to the sleep disruption. Really very interesting. To what extent is the poor cognition in mental illness due to the primary condition or as a result of the sleep disruption? Okay, there's also more connections. Da-da! And neuroscience research. Because of our increased understanding of how you generate sleep, we began to appreciate what the connections between disrupted sleep and mental illness might be. Remember we said, God, it feels like probably was an hour ago, that sleep is generated from multiple brain structures, and look at all these neurotransmitters. And many of these neurotransmitters, or abnormalities in those neurotransmitters, are associated with mental illness. So, for example, defects in dopamine, in schizophrenia, for example. The point I'm trying to make is that if you have a defect in dopamine which predisposes you to mental illness, you will certainly have an impact upon your ability to generate normal sleep. So this whole concept allowed us to sort of think again about the relationship between mental illness and SCARD. And we published that in 2010. So what we're saying is that there are common overlapping mechanisms between psychiatric illness and sleep disruption. Of course, the sleep disruption could well exacerbate the psychiatric illness, and the psychiatric illness could well make the sleep disruption even worse. So what evidence do we have for this? And I'm just going to summarize in the last few minutes. So data that we've published, and we published last year actually, has shown that genes which are linked to mental illness also affect sleep. So a gene that was linked to mental illness in humans, we took that gene and we mutated it and we put it into a mouse. The mouse had interesting defects in its ability to process information, rather like schizophrenia. But what was so fascinating is that mouse, its sleep-wake ability, had been completely smashed. Just like the sort of thing we were seeing in the patients. And we also now have data that genes that are linked to the clock and the sleep systems also affect mental illness. So there are some of those genes we were talking about earlier that make the molecular clock. Defects in those are also associated with predisposition for certain forms of mental illness. So looking for connections between this overlap here, we've got genetic evidence. What's even more convincing, perhaps, is that sleep and circadian rhythm disruption precedes a clinical diagnosis of mental illness. So we've been looking at kids who are at high risk of developing bipolar disorder. They have no clinical diagnosis of bipolar, but we know from family history and a variety of other sources, they are at risk. those kids at risk already show a slightly disrupted sleep-wake pattern. So it's very clear that the psychosis is not driving the abnormal sleep. The abnormal sleep is already there, again, supporting this whole hypothesis of common overlapping mechanisms. And then finally, of course, what about this connection here? Would the sleep disruption affect the psychiatric illness? And my colleague, Dan Freeman in Oxford, has taken patients with schizophrenia, partially stabilized their sleep-wake, and reduced levels of paranoia in those individuals by 50%. So what we've got is a really potentially interesting and exciting new therapeutic target for mental illness. So why do I think all this is important? Well, what I think is exciting is that this sort of understanding of this relationship here, this new depiction of psychiatric illness and sleep disruption, is that it provides us the better understanding of the brain and the genetic mechanisms that are common to sleep-wake timing and neuropsychiatric illness. It's giving us an understanding of the biology of these systems, which is, of course, really exciting and important. More pragmatically, though, you can use sleep and circadian disruption as a biomarker in the early diagnosis of neuropsychiatric conditions. If you have an early diagnostic, it means there's the potential of early intervention and early treatment. And in those kids who are showing signs of sleep-wake disruption, who are at risk of bipolar, if we can try and consolidate their sleep, will we delay the onset of these conditions, or will we knock the brain into a different developmental trajectory completely? And then finally, of course, we can use agents and protocols that regulate sleep and sleep timing for the reduction of symptoms and for the improvement of the quality of life in these individuals. Okay, let me just now try and summarize. What I hope to do in the past, hour and... No, actually, we started 10 minutes late, so it's only been an hour, is give you some sense of the dynamic nature of physiology, these 24-hour rhythms, including sleep. The fact that they arise from amazing structures within the brain. You've got this suprachiasmatic nuclei, this clock ticking away, acting like this conductor, regulating our 24-hour rhythms throughout the body. But sleep also is not only simply driven by the SCN, the master clock, but lots of other agents, lots of other bits of the brain. We then talked about the importance of the light-dark cycle, setting this clock to the external world, and in the process of trying to understand those mechanisms, the discovery of an entirely new photoreceptor system within the eye, which is now having really important implications to clinical ophthalmology. We can redefine the understanding of blindness, and our clinical colleagues in ophthalmology now need to address the role of the eye in regulating the sleep-wake systems as well as vision. We then talked about some real-world problems, shift workers and teenagers, and the fact of working against internal, if the internal clock and the external world are not matched, as you see in these two states, then a whole raft of pathologies ranging from increased levels of stress, cardiovascular disease, immune suppression, and all the rest of it are the result. And then finally, we talked about mental illness and this new appreciation of the relationship between sleep and circadian rhythm disruption and these appallingly debilitating conditions. And finished really with perhaps a new way of thinking about treating these conditions. So there's some perhaps new and exciting potential, and understanding of the mechanisms, the neural mechanisms of sleep are informing new treatments for mental illness. And with that, I'd like to, advertise this. The Sleep and Circadian Neuroscience Institute, we just established that, and so we're now looking at all of these various aspects across the health sector in Oxford. So thanks again for your attention.
Russell, thank you so much. I'd just like to once again thank Russell for speaking here tonight. That was absolutely fascinating. I, for one, would have about 4 hours worth of questions for you, but I know that Russell has to run off quite soon.
We could do 6 minutes.
We have 6 minutes for one or two questions, if anyone.
I've got to get a plane. I do apologise.
If you just raise, just down here first.
Yeah. So we have a couple of people here, then a person over there. Two people here. Oh, and there's this gentleman here. Yeah.
Yeah, the bullet points for your New Scientist article that you made about teenagers, they also true for adults about, say, using an iPad up to the moment you turn off the light and then go to sleep?
Thank you very much. So the question is, what about these iPads and things and the amount of light that these things produce? It's probably not enough light to shift the clock, and particularly if you're getting natural light the next day, any wobble that it may cause will hit the clock, and so you probably don't change the circadian system. although we don't have empirical evidence for that. Where we do have some data is that you'll probably increase levels of alertness. Even relatively low levels of light will increase levels of alertness and therefore delay the onset of sleep. So I would try and limit the use of those iPads and other such devices for at least half an hour before you go to sleep. Because what you really need to do is sort of start to wind down, reduce levels of alertness, because you can't just turn off the wake state and then go into the sleep state. You need to wind down. And in fact, it's a very good point. I mean, if you want to increase levels of alertness, I mean, as a lecturer, I look around a lecture theatre and I see lots of people nodding off and going to sleep. And I realise it's nothing to do with me. It's the level of light. So, yeah, thank you. I think a couple of questions at the back there. And then the lady in the white jacket over there.
Just a question about people with narcolepsy. How does that work?
Yes. So narcolepsy, one of those neurotransmitters we talked about, orexin, which is produced from the lateral hypothalamus. It's one of those agents that keeps us awake. And narcolepsy has been associated with a defect in the neurohormone orexin. And a substance called provigil or modafinil has been developed to override this sort of tendency to fall asleep during the day. And is very effective in treating narcolepsy. The problem is that those alerting pills, modafinil, are being used by night shift workers and a whole range of other people to try and keep awake. The long-term consequences of taking such drugs is unclear. And so many shift workers are saying, oh, well, I'll just take modafinil to keep me awake at night. That's probably not a smart thing to do because the brain is wonderfully plastic. And what it always needs is more and more of the same thing to get to the same state. And whilst these drugs are not necessarily addictive, you may need a modafinil for normal levels of alertness. We don't know, but that would be my caution of taking these sorts of drugs. Yes?
I wonder about your opinion on dual period sleep, where you would sleep for a few hours, then wake up in the middle of the night, do something, and then go back to sleep.
Well, so if you look at the sleep patterns, and it's been well documented in the medieval era, and if you look at societies where there's no electric light, sleep is bimodal. So what happens at dusk is there's a 2-hour winding down. Because remember, electric light, is a modern phenomenon. And in fact, up until the 18th century, people didn't have artificial light because burning, candles was burning fat, which was a valuable fuel. You couldn't afford it. And the cost of a candle, even in the 19th century, was almost the cost of a working man's daily wage. So we were driven by the natural light-dark cycle. And at dusk, there was a 2-hour winding down, 4 hours of sleep, and then you'd wake up and wander around for half an hour or so, and then another 4 hours of sleep, and then a 2-hour winding up. So in a 12-hour episode, you'd have 2 sort of bolts of sleep, which is very interesting because, of course, in modern society, we've squeezed this together. And so we're lucky if we get 8 hours. But it may well be that if you wake up in the middle of the night, it may be part of that throwback to an earlier sleep pattern, which was clearly bimodal. In fact, in the medieval era, people talk about, I had a wonderful first sleep. It was well documented and well known. And I think when people do wake up in the middle of the night, there's a tendency to think, oh my God, I'm never going to get back to sleep. I'll turn the lights on, I'll have a cup of tea, and of course, that's daft. What you need to do is think, okay, this is part of my ancient biology. I'll be cool about it. I'll be relaxed, and I'll probably fall back to sleep again. I think we probably have one last question from the lady over here.
Lack of sleep in an individual, does that, over a period of months or years, how long does that take to impair possibly the vision of the individual?
I don't know about the vision, as in the performance of the eye, but you're quite right to raise the importance of long-term, and I don't think I did that sufficiently well. Where we talked about cancer, for example, there's been nice studies on night shift workers in night shift nurses in Denmark, and they had high rates of colorectal cancer and breast cancer. Data is very clear, but these were individuals who had long-term, they've been on the night shift for more than 10 years. So I'm not going to say if you do night shift, you're going to get cancer. That's not. But it's the long-term accumulative effects. And in fact, it's probably fine to be fairly flexible, but it's where you're hitting the body day after day after day and driving physiology so far out of its normal range, you're precipitating these illnesses. I don't.
Sorry, the interventions that you said that would help the individual to sleep. You said, what were they other than these? You said avoiding sleeping tablets.
Well, I think it's this whole concept of sleep hygiene. So you start to wind down, and so the bedroom really needs to be dark, and it needs to be slightly cool. I mean, most bedrooms are well overheated. They're too hot. And in fact, part of the way you go to sleep is the loss of core body temperature. You know, remember that graph we saw earlier? If you prevent that, then it's more difficult to go off to sleep. And there are conditions called vasospastic disorder, very common in women, whereby the blood vessels of the hands and feet can't get bigger, they can't dilate. So you can't shunt blood from the core to the periphery to lose that heat. So cold hands and feet stop you actually getting off to sleep. And so our grandparents, what do they say? Bed socks and mittens and things. Well, of course, it will keep your hands and your feet warm, which means the blood vessels will dilate, so you can then lose that heat. So again, don't be too hot, but also your hands and feet must be warm. Dark. Start to wind down well in advance of trying to go to sleep. Minimize your light exposure. Don't take caffeinated drinks if you can possibly avoid it in the afternoon, after lunchtime. And also do things, if you just listen to your body. What are the things that start to relax you, wind down? Do you have a sort of a habit, reading a couple of pages of a novel, whatever it is, and you just start to take sleep seriously. And do all of that before you resort to any medication. Certainly before you go to sleeping tablets or alcohol. And I'm sorry, I do apologise. I have to get this.
Thank you to everyone for coming along tonight. Please, thank you, Russell Foster.